All right, let's go ahead and solve this problem from the McGraw-Hill thermodynamics book, problem number 740. So in this problem, we are going to determine the work and heat transfer of a thermodynamic process, which is an isothermal process for a closed system. So let's go ahead and see that what are the state of initial state and final state of this isothermal process. So for this problem, we have state 1, right, and state 2. So first of all, this cycle is this process is a isothermal process. So the temperature of state 1 and temperature of state 2 is the same. T1 equals to 40 degrees C and T2 equals to 40 degree C. So at state 1, this refrigerant pressure P1 was 320 kilopascal and temperature was 40 degrees C, and then it undergoes an isothermal process, and also the system is the closed system, and then final state, the quality of that refrigerant is 45%, right? That means that X equals to 0.45, right? So let's go ahead and look for the the diagram, the table for refrigerant 134A, and then from this condition T1 and P1 and T2 and X, we'll get the relevant properties to determine the heat transfer and work. So if we go if we take a look on the table, so we go to the table A13, which is the saturated refrigerant, right, which is the saturated refrigerant, excuse me, which is the saturated refrigerant 134A. So for our case, we got the pressure 320 kilopascal, right? This is the pressure, and that for that pressure we see that the saturated temperature is 2.4 degrees Celsius. That means that 40, but for our case we have the temperature is 40 degrees Celsius. So 40 degrees Celsius means that it's already went to the saturated superheated region, right? So for superheated region, that means that for state 1, 320 kilopascal and 40 degrees C, we have to go to the superheated refrigerant table, which is the table A13. So from the table A13, there are multiple the table within this table, but for our case the pressure is 320 pascal. If we convert it in megapascal, then it will be 0.32 megapascal. So that means that this is our property table. So from this table we'll look for look for the from this table we'll look for the properties which are based on the pressure and the temperature is 40 degree C. So for 40 degrees C, we will have this line, right? So basically we'll use this this one, and then let's go ahead and plug in these values. So I already take the screenshot of this one, so let's use those the diagram. So this one, so if I crop this one, so I just need this table, right? Actually I have to use the temperature. Okay, so for okay so for 40 degrees C, so for 40 degrees C, I have the so this is the 40 degrees C line. So for 40 degrees C, record the I'll record the specific volume, and I'll record the internal energy, and I will also record the entropy, right? So let's record the internal energy or the specific volume. Okay, so the specific volume small v1 equals to 0.07530 meter cube per kg, right? And for internal energy u1 equals to 261.62 kilojoule per kg, right? And the entropy at state 1.0452 kilojoule per kg Kelvin. So we got all those the property at state 1. Now let's go ahead and determine the properties at state 2. So state 2, we can see from this x value, which is the meaning of this, it's already in saturated condition, right? So it's no longer in superheated region. So for saturated condition, we'll look for table A11, right? And from that table we'll get the value of state all the thermodynamic property. So I already took the screenshot of that table too, so let me import this table and show it to you guys. So it's I have to use the pretty much the whole thing. Anyway, so for state 2, we know that for state 2 we have the temperature, isothermal temperature, which is this 40 degrees C. So for 40 degrees C, we'll calculate we'll take the internal energy and the entropy. So for state 2, let's also record the specific volume as well. So specific volume Vf equals to 0.000872 meter cube per kg, right? And then Vg equals to 0.019968 meter cube per kg, right? And we do have the internal energy UF equals to 107.39 kilojoule per kg, and we have UFG equals to 143.61 kilojoule per kg. And then we also have the entropy SF equals to 0.39493 kilojoule per kg Kelvin. And then we do have the entropy of the saturated liquid equals to liquid vapor SFG equals to 0.052059 kilojoule per kg Kelvin. So now we got all those property, right, for state 1 and state 2. So for this thermodynamic process, it's an isothermal process, and for this isothermal process, we just derived this derived the equation for entropy change and the heat transfer. So the equation was nothing but Q equals to T naught times S2 minus S1, right? So if the temperature is a constant temperature, then the heat transfer will be this. So for this case, we have the T naught equals to 40 degree C. However, everything S1 and S2, if you look carefully, everything is expressed in Kelvin, absolute temperature. So we have to convert this temperature 40 degrees C to the absolute temperature in Kelvin. That means that plus 273. Now this is in Kelvin, and then times S2. We have the we have to calculate the S2, and S1 we already have. So let's just calculate the value of S2, right? So S2 equals to SF plus X into SFG. So we have SF equals to 0.39493 plus 0.45 times 0.52059. So for S2, we have S2 equals to 0.629196 kilojoule per kg times Kelvin, right? So if we plug in this value in this equation, right, in this equation, then we'll get the heat transfer of this thermodynamic process. So heat transfer is equals to 313, right? 313 Kelvin. Let me write this Kelvin, and then S2 equals to 0.629196 minus S1 equals to, we have here 1.0452, right? The unit is kilojoule per kg Kelvin. So this Kelvin and this Kelvin will be omitted. So now if I simplify this one, the heat transfer of this thermodynamic system will be minus 130.20 kilojoule per kg, right? So this is one answer, right? Heat transfer of this system. Now we have to determine the work done to the system, or work done by the system. So here we can see that there is two things they're asking. One is that heat transfer, another is that how much work required for this thermodynamic system. So for work, we know that the relationship between the work, energy, and the heat is expressed by the first law of thermodynamics. So first law of thermodynamics, it's relating the work, heat, and energy, right? Energy. So which is nothing but, if we have a system and that system has work energy and the heat, then the system energy balance of this system equals to Q minus W, equals to change in the kinetic energy plus change in the potential energy plus change in the internal energy, right? So for this particular system, we see that they use refrigerant 132A, and in from state 1 and state 2, it's a closed system, and we don't see any velocity, or we don't see any kinetic energy change, right? That means this term is zero, and there is no potential energy change. That means there is only change in the internal energy. So from this equation, we have the we already know the value of the Q from this equation, and we also know that the internal energy of state 1 and state 2, so we can calculate the work done by this system. So before that, let's simplify it more. That means U2 minus U 1. So since they're asking for the mass basis, that means I'm gonna go ahead and multiply this system, divide this system by mass. So that means it will be small q and small w equals to u2 minus u1. So for the state 1 we already know the internal energy, but for state 2 we have to calculate the internal energy. So for state 2 internal energy u2 equals to nothing but uf plus x times ufg. So for state 2 u2 equals to uf plus x times ufg. So we do have u2 equals to, we do have the value, all of these values. So 107.39 plus 0.45 times 143.61, right? So we do get the ut equals to 170.172 kilojoule per kg, right? So this is our u2, and we already have the u1 for the state 1. So now if we plug in all those value u2 and u1 in this equation and also the q, we have the, let's plug in all those value. So we got the q equals to minus 130 kilojoule per kg, and then minus w, and we do have the value of ut 172 minus u1, which we have in this case in this case 261.62. So if we simplify this equation, right, then we'll get the value of w, right? W equals to minus 40.38 kilojoule per kg, right? So this is the answer for the work required for this system. So we notice that one thing in common for both of the heat and work, it's this negative sign, right? So if you take a look here, then it has the negative sign in work, and also for q we have the negative sign. That means this negative sign for q is nothing but it's representing the heat output. That means it's lost, some heat is losing, right? It's losing the heat of this system. But for this for work, this negative sign is representing that is work required, or work is input of this system. Or so to run this system, some sort of work is required for this thermodynamic system. So that's the answer for this problem. So this is answer, and this is the